till that stops. Let me tell you a couple of announcements first, since we are recording. You probably all work on Fridays or otherwise disposed, but there is a program over here, 9:30 to Friday morning. It's a UAB troupe or traveling group of performers, singers, artists of some nature, and they will be doing Broadway hits, and it's supposed to be quite nice. So if you are free Friday morning, 9:30, the A.G. Gaston Auditorium is where they'll be performing. And okay, now it should start, I hope. All right. Another thing, and I don't know if any of you are available for this either, but well, let me ask this. If any of you are graduating either this term or next term, this is the time to get your graduation application started. If you're graduating this term, it better be turned in very soon. But if you're graduating next term, this is the time to get it started because you need to get with what they call a, let's see, please come through this time. They need to get no signal. What in the world is wrong with this mess? There we go. Now why, I don't know. All right, at least we have this now. So and in the future, any of you who may be graduating, always remember it's a good idea to start the graduation application the term before you're scheduled to graduate. That way you can find out if there's any courses missing that you weren't aware of. You can, if one doesn't show up on the schedule you need, you can talk with the department chair or your advisor can, see if you can get those scheduled so you can graduate on time. Also, they're looking for note takers in student services, and they were also looking for tutors in the Space Center. Okay, math, English, Spanish, computer science, and biology. So some of you might be very good at some of those areas. Okay. All right. Yeah. All right. I heard a request. The request lines were open. And what was that request? On what? Okay. Just a question about test 2. Okay. Hold on just a minute. Let me get test 1 on top. Test 1, 1, 1, 1. All right. Test 2, which one? Number 7. All right. And what's your question there? Okay. Let's do what I can on this one. Did you look and couldn't find any quite like it in the text? So this is test 2. Let me get my pen set up. Where is it? There it is. Okay, test 2, number 7. A pump is capable of developing 5 kilowatts of power. 5.0 kilowatts, and they have already told us this is the power. Okay. How many liters of water per minute? Okay. So the question is, now, here, okay, you might want to name a variable. It doesn't have to be one of our regular ones because this is liters of water per minute. So you can make up any variable you want there. What variable would you like to use? Doesn't matter to me. Pick a letter, any letter. Not P, probably not K, not W, not L. Pick a letter. X, why not? Let X, whoops. Okay. Let X equal the number of liters per minute of water. Okay? That's what we're going to be looking for. Okay? Liters per minute. Okay? Can be lifted a distance of 25 meters. Okay? So you're going from some location here to some location here, and that's a lift of 25 meters. Okay? So what you want to name that one? The height there. You can name it Y, you can name it H, you can name it S, so they named several things. What did you want to call it? Second? H, okay, let that be H, okay? So H is equal to 25 meters. Okay, now, and 1 liter of water has a mass of 1 kilogram. So 1 liter H2O equal 1 kilogram. So therefore your X here could also be expressed in number of kilograms per minute, okay, of H2O. It doesn't have to be liters, it could be kilograms. Same number because 1 liter is 1 kilogram. And that's a mass unit, okay? Now, tell me something. What is power? Whoa, what in the world was that? Huh? Okay, it's work. Now, this W is not that one. That's kilowatts. That's a unit. This is work divided by time, okay? Now, look, we've already got our time in the problem. So, let's talk about what work is then. Force times the distance, okay? And that's divided by time. All right, we've got our distance. We're calling H, okay? What is force? Say again? Newtons, yeah, force in newtons. And how do we get it? What is that?
Force is mass times displacement.
Not displacement. Yeah. This is mass times the acceleration. Now, the force we're talking about here is the weight of the water, right? So it's the mass times the acceleration due to gravity, so that's going to be mg. So here we have mg, I'm going to put it as h because that's what we had here, over time, okay? Well, the mass per unit, our x is this mass per unit time. You see that? Kilograms per minute. You know what G is, you're given what H is, and then you'll go back in here and I think that's pretty much everything. So what you'll, this is what you're looking for. This is your X, okay? And you know what the power is, so there's your equation. P, which you know, is equal to XGH, where X is this kilograms per minute. Does that make sense? You know G, you know H. So I think you can solve for X. Is that enough? All right, good deal. Any others? Say again, 10, same problem set. Okay. A 55-gram bullet is fired vertically with an initial velocity of 123 meters per second. Okay. All right, if I erase this one, because I'm going to need a lot of white space for this one. Can I erase this one that's on here? Okay. I can leave it up if any of you need it a little longer. Anyone need it longer? Huh? Okay. Okay. Got it? Okay. All right, to erase? All right. A 55-gram bullet is fired vertically. So here is the rifle, pistol, whatever it is that you're firing from. You're firing the bullet vertically. So here goes the bullet. Okay? Now, the mass of the bullet is equal to 55.0 grams. Now, most of the time, we deal in kilograms, but grams is fine too. Initial velocity, V0, VI, which do you prefer? VI, I prefer that too. But I'm so used to writing V0 because a lot of times the book does. VI is equal to 123 meters per second. Okay. 3 parts of this. And by the way, number 10 only has one line, so you can put A on that one and then B on the line beneath it and C on the line beneath that. I think that's the only one that's like that. But if you ever need an extra line, just put another line underneath it. Okay. Now, this bullet, when it first leaves the barrel, it's traveling at that initial velocity. What happens is the bullet is going upward? It's slowing down. So, can you tell me the bullet's speed at the very highest point? You should be able to, because it's not going any higher. Hint. You know what the velocity is then? Yeah, okay. You know what we're talking about? Okay. Okay, the bullet leaves the rifle, the gun, whatever it is, at 123 meters per second. As it goes up, it slows down, and slows down, and slows down, and slows down, until it reaches its highest point. What's its velocity there? Don't say it out loud. It's slowed down as much as it can until it starts falling. So what's its speed? You got it? Okay. All right. Good. All right. Now, the next question says, what maximum height does it reach? Okay. Now, that's from the formulas that we use with kinetic and potential energy. And we had a, this is chapter 5, wasn't it? 8. Okay. Conservation of mechanical energy. And there is the formula that we can use for how high, isn't that what it asks? What maximum height does it reach? They have that formula at the bottom, that V, this is on page 219 if you got a book. 219, V is equal to the square root of 2GH. Okay? Now, this V is the velocity at the bottom. Okay? This is the velocity down here. The 2 is 2, okay? The G you should know, right? And the H, that's what you're looking for. So you have to rearrange that formula there to solve for H. You know how to do that? Yay or nay? No? Okay. If you're wanting to solve for H, what's the first thing you got to get rid of? The square root sign. And how do you undo a square root? Square, okay? So if you square this side, you lose the square root, right? Okay? So you've just lost the square root sign, okay? Now what do? You want to isolate the h, so you see how to do it from here? This is what you're looking for. Say again? Yeah, divide by the other things and you got it. And I think that should answer your problem for h, right? Okay? Now, they want you to use another formula for it coming down, okay? But you really don't need to, because at the same rate it was losing speed going up, it's going to be gaining speed coming down. So you should know what speed it is at the bottom. No, that's at the top. I'm not saying when it hits the ground, right when it's the same level that it was here. Hint. Say again? Okay. Yeah, okay. So you see why? Because at the bottom, it's all kinetic energy. Energy of motion. So velocity is what's controlling that. No potential energy at the bottom, because that's as low as it can go. At the top, it's all potential energy. No kinetic energy, so we know what the velocity is, right? So when it comes back down, it's back down there, all kinetic energy, no potential. Okay? Okay, it wasn't quite as bad as you thought, right? Maybe worse. Okay, all right. All right, any others? All right, let's move then back to, okay, I think that's where that goes. Chapter, all right, to clear this out of the way? Okay. Now, we're in chapter 12. We had been talking about stuff in 12.2. We're on the top of page 316. Okay? And let me see if I can pull up the other slide. Yeah, that's where we begin tonight. Okay. We were talking about, on the previous page, elasticity. Anyone remember what elasticity means? It's one of the characteristics of a solid.
The ability of an object
to return to its original shape. Okay? Now, here's a spring. Looks like a pretty substantial spring, right? Now, if you were strong enough to stretch that spring or put a big enough weight on it or did something to it to stretch the spring, you can stretch it, and as long as the spring comes back to the original shape when you release, you're in the range of elasticity, returning to the original shape. However, there is, and I think you've probably all done this before, maybe a spring on a pen. In fact, I think, I'm not going to look for it now. I had a spring in a flash drive, and the cover came apart, and the spring came out, and I don't know what happened. But anyway, it's not going back again. Okay. You may have had a pen, a ballpoint pen, and somebody was playing with it, a kid or something like that. Took it apart and then stretched the spring too much, and it didn't come back. That's past its elastic limit. This spring here is stretched, it says near its elastic limit. As long as it hasn't exceeded it, it will come back. But what happens if it exceeds it? It's not coming back again. It gets sprung, okay? The spring is sprung. No longer coming back to its original shape. It's stretched beyond the elastic limit. Now, if you went far beyond the elastic limit, you may actually break the spring completely. I mean, not just make it so it won't come back to its original shape, you actually break it, okay? And if that happens, you've reached the fracture limit. It is now fractured. So elasticity is that ability to come back to the original shape. Springs have this. Other devices do too. I wonder if either of you ever have hung on a rim. Yeah. I thought you probably had. And fortunately, it returned to the original height. However, I've seen in some games when it didn't, okay? When Shaq hung on it too long, it probably wasn't going to come back, okay? He passed the elastic limit. Or a couple I've actually heard of, the whole thing fractures. Then, say again? Yeah, so it could happen. So that's what we mean by elasticity. If it returns to its original shape, fine. Okay. Yes?
Does the material that it's made of depend upon whether or not it has elasticity, or do all objects have elasticity?
Okay, good question. Probably, don't lead this with probably. Probably all objects do have some elasticity, but some it may be very minor. A piece of glass will probably, if you threw, say, a water balloon at it, and it might give a little and then go back. But if you threw a rock at it, it's going to fracture. So glass is one that has a very, very low elastic limit and very high or very close fracture limit. It's going to fracture really quickly. So all objects will. There are some types of steel they actually call spring steel because they do make springs out of them. And they have very wide elastic limits. It goes for a long way. There are other things like steel is made out of iron, but if you have cast iron has a pretty low elastic limit. It probably will give a little bit, but it's going to fracture before before you hit it too much. Okay, whereas a spring steel will do otherwise. So yeah, there's a wide range of elasticity. In some materials, they develop to have a wide range of elasticity, and for good reason. Okay. Now, the next concept here, and they just sort of move into it without too much ado here, they start talking about stress, okay? Now, stress isn't, oh, goodness, I have 4 tests this week, what am I going to do? That's not the stress we're talking about, though sometimes it might feel like that. What we're talking about here with stress, I think, I hate to go back, I'll just write it here. Let me get my pen back. Okay. The stress they're talking about here is what we refer to as force per unit area. Stress, force per unit area. The applied force divided by the area over which it acts. Okay? Now, if I were to take this book, okay, and if I were to drop this, I'm not going to, okay, if I were to drop this book on the foot from this height, okay, the book has a certain weight, height, it's going to release potential energy here, the kinetic energy at the bottom, and it's probably going to feel it, right? How about if I did this? Same book, same height, and that hits your foot, more or less. Don't hurt worse. Same book, same energy, same force, same everything, except the area which is striking your foot, small area here, big area here, right? So this would be illustrating stress. Same force, smaller area, more stress. Because a smaller denominator makes a bigger number, right? And a bigger denominator makes a smaller number. 1/10 is a lot less than 1/2, right? Small number, bigger space. So if it's a small area. So that's what stress is. Force per unit area. It goes by other names. Pressure is another way to say that. Force per unit area. One of the there's so many units you can use for pressure or stress. Okay? What is the SI unit for force? Newton. And area would be what in SI? Meter and meter squared, because length is a meter and length by length is area, square meter. Hey, wait a minute, folks. A square meter is basically the almost lower half of this door. Okay, this is a good approximation of a square meter. Most door handles or door knobs are about a meter off the floor, and that's about the same width as it is height off the floor, so that would be a square meter. Goodness, that's a lot of area. So to have any measurable force on that area, you're going to have a lot. I mean, that's going to be a very low stress because it's such a large area. Okay? So, Newton per square meter, when I just opened the door there, that probably changed the pressure in this room by a few pascals, and yet no one can sense that because it's such a small amount. Because, see, your denominator is huge there, a huge area. Okay? So that would be a small, and that is what we use. A Newton per square meter is a Pascal, named after Blaise Pascal. Now, it's not just P, it's PA, because I can't remember what the other unit is that uses P, but some other unit had already taken the P, so it's a PA, Pascal. Okay? Now, in U.S. customary, what do we measure force in? No, that's work, but pounds. That's the part that's force. Pounds. Now, most of the time in U.S. customary, we measure length in feet. Here we're going to use it inches. So rather than square feet, we'll say square inches. Okay? Pounds per square inch. Have you ever heard of that? Second? PSI. That's exactly right. PSI. Okay? Any of you know what 1 atmosphere of pressure is in PSI? About 14.7. Well, this is pretty amazing to think about. What we mean by an atmosphere of pressure, we have a whole atmosphere of air above us, right? Does air have any weight? Yes, it does. You may not think of it as weighing much, but it does, okay? I've seen this experiment before. You put a deflated basketball on a scale, okay? Weigh it. And then pump it up with air. Same basketball, put it on the scale, it'll weigh more because air has weight. You don't notice it, but it does. And the whole atmosphere above you is going to have 14.7 pounds per square inch. Now, your two thumb joints together like that is about a square inch. And if you think about how many square inches are on your body and multiply that by 15, that's how much weight you have pressing down on you. Wow, that's a lot of weight. But you see, we have muscles, we have good skeletal structures, we have blood pressure, so we're pumping, we have pressure out. In fact, if you scratch yourself, the blood actually comes out. It doesn't go in, okay? So that means you got more pressure inside than out. Now, my mom used to do this, and it was really scary almost to look at. She could take the skin on her hand, pull it up, and it would stand there for several seconds. Mine takes a little longer than it used to go down because I'm not as efficient with keeping the pressure up. Her turgor pressure, blood pressure, was not blood pressure, but the pressure in her body just wasn't as good as it used to be. It probably goes right down. Mine stands up for just a little while and then goes down. Okay, so we have pressure on us all the time. I don't know if you ever thought about this, but I think probably one of the most dangerous jobs that's ever been attempted, and done successfully, by the way, was, if y'all remember, I don't know if you remember this or not, we have an International Space Station now, okay? Really an elaborate thing, an amazing thing, and it's really been doing great for many, many years. Before that, we had tried to put a space station up there, and it did okay, but it didn't maintain its orbit. It crashed into the sea. So the Soviets, that was back when it was Soviet Union, they had a space station that stayed up there longer than ours, so we were all using their space station. I mean, you know, we would send astronauts up with their cosmonauts, you know, it was, people were pretty much working together fairly well in space anyway. So, we had the shuttle fleet, if you remember that great big thing that would land, you know, take off on top of a rocket, and then it would fly, it would lose the stages of the rocket, fly, and then when it came back, it would come back in and land like a big, big plane. Well, no one else had that. So we would use our shuttle fleet to move people and equipment back and forth. But when they weren't doing that, the Russians used basically robotic cargo vessels. They'd send them up there, and then they'd all be controlled by computers and get it to come to the space station and bring supplies. Well, one time something went wrong, and the cargo ship, let's call it, came in too fast, too strong, and really whammed into the space station and damaged it big time. So badly, they had leaks in a lot of it, so the crew had to get into a tiny little safe space. I think there were like 3 or 4 people up there then, and they were all crammed into this really tiny little space. And they were having to stay there, okay? They couldn't go out because there was no pressure outside. Well, what happened, we sent up people on our shuttle fleet, people and equipment to repair the space station and get it back. Well, where that cargo ship had come, there was jagged, broken, bent, twisted metal. And it probably was not too safe. And those astronauts were out there trying to repair that, you know, floating around in space, you know. Now, if you can imagine, they're in these big, bulky spacesuits. Why do they wear big, bulky spacesuits?
To weight them down?
Not to weigh them down. There's not much gravity there to do that. But if you're getting close, it's to pressurize their body. Because you see, out there, you don't have an atmosphere of pressure above you. And you've got in you about 15 pounds per square inch of pressure pushing outward. And when you don't have a atmosphere above you, now there's nothing to press against you. Okay? So they were out there, and that's the main thing those space suits do. The other thing, they're silvered, and so they reflect, because you see, our atmosphere does something else for us. It blocks all that harmful radiation. There's nuclear explosions going on the sun constantly. Major hydrogen reactions, okay? I mean, major reactions, sending off all kinds of radiation. And if we were exposed to that, you're going to be dead pretty soon, because your body cannot handle that. Our atmosphere blocks the vast majority of that radiation. Okay, the only thing it lets through is visible light. Okay, a little bit of ultraviolet light gets through, and UV light is what causes skin cancers. Okay, sunburns, cataracts, wrinkling of your skin. Okay, it's not good stuff, the ultraviolet, and that's the mildest of the other. The visible light is fine, but the ultraviolet is not, and why we get out there and spend as much time in it, I don't know. Used to think it was healthy. It's not, okay? You need light, but you don't need that much ultraviolet light. Okay, so that's the other thing the spacesuit does for you. The main thing it's doing is pressurizing. Okay, so here they are working around this thing with jagged pieces. If some jagged piece of metal had ripped their spacesuit, and they lost that pressure, then 15 pounds per square inch of force of all the fluids, gases, and liquids go spewing out. They'd be dead in an instant. Radiation would have a chance to get to them because they would, never don't even want to think of it. But that would literally happen. So that had to have been one of the most dangerous jobs ever attempted, but done quite well. It's when they repaired the Soyuz space station. Okay, I couldn't think of the last word. All right. So PSI, that's why I brought that up. And that was that illustration. Now, here's another illustration of that. Here we have a brick, okay? And this brick is laying on the table, okay? Now that brick and that brick are identical. 8 centimeters this way, 16 centimeters that way, 6 centimeters that way. 6 centimeters this way, 8, 16. Identical bricks. The holes are identical. Everything's identical. Identical weight, which is exerting more pressure on the table. The one standing up, because it's the same force, weight, but a smaller area. Much smaller area down here. That's 6 by 8, so that's 48 square centimeters. This one is 16 by 6, which is what? 96 square centimeters.
And did you say the smaller denominator means more stress?
Yes, more, yeah, because more weight, same weight, but smaller area. So for a smaller area, more stress or more pressure. Okay? Now, another sort of, they skipped this one. It's in the text. And I thought they were going to show the slide, but they didn't. I was dancing with my darling, okay? And she had on sneakers, good for her, okay? And she stepped on my toe, probably my fault, not hers, okay? How bad was it? Not too bad. But I was dancing with my darling another night. She had on spiked heels. Same darling, by the way, okay? Same weight, same force. And she stepped on my toe. Not so good. Spike heel, tiny little area, same force per unit area, huge. Sneakers, I won't say how big her foot is, but force over a much larger area. Same force, larger area, much less stress or pressure. Okay. They actually do the math with these, and they told you the force or the weight was 12 newtons. They don't show this on here. It's at the top of page 317. The area of the block over there, the brick over there, the first brick, is 16 centimeters by 8 centimeters. That's 128 centimeters. I couldn't do my math. Sorry about that. That's not right. It should be by 6. The way they have it done. If you laid it on its side this way, then that would be 16 by 8. So I think I did do mine right. Okay, but anyway, the stress is, if you laid it on its side there, that would be 938 pascals. Okay? Because it's not centimeters squared, it's meters squared, okay, for a pascal. So that's 938 pascals. If you did it on the edge like that, where you only have 6 by 8 or 48 square centimeters, then the stress or the pressure is 2,500 pascals. Way, way more pressure. Same weight, but smaller area. So you increase the pressure or the stress big time. Okay. The shoe example they give, 160-pound woman rests her weight on a 4 square inch heel. That would be about, well, I think that's a little bit, well, no, that would be pretty close to 4 square inches, okay? That would be 160 pounds divided by 4 square inches, 40 pounds per square inch, 40 psi. If she did it on a 1/4 square inch spike heel, then it's 640 psi. I'd much rather have the 40 psi on my toe than the 640. Okay.
So what's the more common unit with this? Is it Pascal or is it PSI?
It depends on where you're from. Okay. We use PSI a lot in the U.S. and most of the rest of the civilized world, they use pascals or kilopascals a lot. Yes. Okay, where are you talking about? 12. Oh. They just told you that. Imagine a brick. If you go back to page 316, the last paragraph is above that picture of the bricks. Imagine a brick weighing 12.0 newtons.
Yeah, I was just looking at the figures. I need a diagram on it.
What's that?
I don't see what it adds up to 12. So.
Well, yeah, they just said the brick weighs 12 newtons. Yeah. It's just like I weigh, I'm not even going to talk about it. Yeah. Right. Okay. Yeah. The newton is your weight or your force. Right. Okay. Just like the woman was 160 pounds. Okay. She didn't want to tell that, but it was. Okay. Okay. So we did that. So there's one way of that we measure what a solid is doing is by the stress or the pressure. There's another way, and this is tension, okay? And they sure don't leave us much room to write there, so I'm going to back off. Yeah. I'll write here. This is stress or pressure on that one. Here's what tension is. Tension is a stress. It's a force, but it's caused by two forces acting directly opposite each other. So there's two types of tensile force. One is a pulling apart, and one is a pushing together. Remember the one back here where the spring was stretched until it's almost straight, and you continue to stretch it. And if you'll notice the diagram here, see the spring has a certain diameter here, but where the weak point was when you pulled and pulled, you were doing tension on this in opposite directions, and that's actually stretched the metal, and it got smaller diameter, and you'll see this happen sometime, and then finally it gets so small that it breaks. Okay? So that is a tensile. Tension is a stress, but in an opposite direction. Now that's one type of tension. There is another type, and that's a pushing together. Again, in opposite directions. Okay? I guess the best example, in the book they show a tug of war, that's a tensile pulling up against each other, and very seldom will the rope break. Most of the time the people break, okay? But then the other, the pushing together, is this one. Here you have the weight of the bridge down, but the piling is pushing up, so that's a tensile force, but it's again in opposite directions, but not opposite this way, and that's also a measure of tension, okay?
So the weight is the pile, not the water, like the water.
Okay, yeah, the pile is driven down way into the sea floor and then some. I mean, it's they drive down till they're on rock or got so much steel or concrete under there, and then they build on top of that. Otherwise, that's going to sag. Okay, so the piling goes way down. I don't know if you've ever been near a place where they've been building, say, a large building. Now, a house, and not too large a building, they just dig a footing, and then they put rebar in it and pour concrete, and they get lots of support that way. But a real tall skyscraper or things like bridges and stuff, I mean, remember the pile driver that we did in the early? They they force that thing down until they basically can't get it to go any further. And once they've done that, they know they're about as good as they can get. Okay? So this was probably built with a pile driver until they couldn't get it to go down any further. Now they think they're on bedrock or something pretty close to it. Okay? So that's a tensile force in the opposite direction. Okay? So that's compressive. Okay. So tensile forces are usually the pull apart. Compression are when they push together. Tensile is pulling apart. Compression pushing together. Okay. Stress caused by two forces acting directly toward each other, not away from each other. Okay. Now, there's yet and here's another example. A column under the New Clark Bridge crossing the Mississippi River is in compression. The weight of the bridge here, the force upward of the piling there. All right. Now, this is an example of a shear stress. Okay? A shear stress is a sideways kind of thing. You have a force here, another force down here, but they're separated by a distance, so they create a distortion. That's called a shear stress. Okay? And that's the next one they do. Shearing is a stress caused by two forces applied in parallel but opposite directions. Tension is in the same line, or compression is in the same line. A shear is offset, so you get a twisting motion. Okay? And you see the book is distorting itself, okay, as you press on it that way. Now, the next is a torsion, which is a stress, but that's related to twisting motion. And remember back when we talked about work measured in foot-pounds, I said there was another thing measured in foot-pounds, and that was called torque. And torque and torsion come from the same root. This is a twisting force, okay, as in screwing or bolting something together. Much stronger than just driving a nail. The screw actually holds it much because you got that torsion in it.
So when you strip a screw, when you're doing it,
yeah.
When you strip it, is that still torsion or is that shearing at that point?
Okay, yeah, that's a very good question. You said when you strip it, yeah, the odds are that you've either, it could be the screw itself, you've sheared off the flanges, or more likely the material you're going into has broken off the thing that held. Like if it was wood, you have now torn up the wood. If it was real soft wood and you over tightened it, now you've ripped the wood so there's nothing for the flanges to hold on to. That's usually more common, but metal on metal, you could strip it the other way. Okay. We have, our old house has an upstairs, so there's a railing on the stairs, and of course the wall is plaster. And plaster, doesn't have a lot of strength of material, you might say. And I think, or we think it's I think there's two culprits. When Karen's dad comes to town, he's a big man, and he puts a little too much on that, and he almost always works the bottom flange in the wall, so it's like this. We think the cleaning lady, when she's carrying stuff up and down, she must put a little bit on it, because quite often after she's there, it's loose again. So I have to go in, and there's nothing else to do. So what I do, and this is from Karen's grandfather had this technique, where you screw it in. Now, there's nothing holding it. So what I do is take a match stem, wooden match stem, push it into the hole where the screw goes in, and then screw it in, and the wood spreads out and fills up the gap a little bit better, okay? But in time, it's going to happen again. So you just are creating something, yeah.
Well, I know I've seen my husband use those screws that go in, and then they have the thing that
Yeah. Now that's for drywall because there's nothing back there. So now you're just pulling against the back of the drywall, and that's what holds it in place. Yeah, you had a question, sir.
Making sure I understand, her question. With the shear, it's more pushing, whereas with the torque, it's
Twisting. Yeah, and yeah. But the wood right next to the screw really can't tell which is doing. It just is getting sheared or the torque is lost the ability to do the torque. Yeah. So yeah, you're right. The torsion is a twisting motion. Shearing is a lateral motion like this. Yeah. It's lateral motion but separated by a distance. So yeah, you're right. The next was the bending, and this was the example I gave a while back on putting a board between the two tables and then me trying to walk across it. Not going to work too well, okay, unless it's a mighty thick, strong board, okay, because this guy sitting on it, that's bending. That's both tension and compression. The tension is pulling this way, the compression where he's sitting. So, in other words, when it bends, the bottom part of the bend is being tensed, and the top part of the thing is being compressed. So that's what they meant. It's a combination of tension and compression. Those are just terms you might need to know. Now, stresses are the forces. I think of them as the verbs, the thing doing the action, okay? What results from a stress is what we call a strain. And back on the elastic stress, if it pops back to its original shape, the strain is elastic strain. If it gets deformed, we call it a plastic strain. And then if you actually break it, it's a rupture or a rupture strain. Okay.
And our bodies can have that, right?
Oh, yes.
I've had back surgery because, a disc herniated. That's what happened.
Right. Exactly.
It gets too much strain.
Exactly. And that happens for a couple, and I mean, are any of you nurses? Yay or nay? No? Okay. It's historically, and I hope it's getting better now, but nurses, especially I think like emergency room nurses, operating room nurses and stuff like that, quite often they're required to lift at such terrible angles. People who have fallen, people who have, collapsed, there's things like this. And usually my sister-in-law is almost an invalid because her back, she has had so much work done on her back because she did. And I see some of the nursing instructors here. Now, I don't know if it's all back, but there's at least one that uses a cane regularly. And they are just notorious for having, reaching over a bed and lifting. That's a terrible, terrible strain to do to your, a stress that you're putting on your back, and that it can rupture disc, misalign vertebra, the whole works. So I was going to say, if any of your nurses, be very careful. And when you're in places like that, I know it's probably not comfortable wearing those back braces. I think would be a fantastic idea, and if they don't require you to, they should, because you're losing good quality people because of back injury. All right, finally we're at a place to do an example. Okay. Oh, here is the shear forces. One force in this direction, one in that direction. They're parallel. If they were like this, those would be compressional forces. But when they're separated by a distance, that gives them the shear nature. Okay. Now. Oh, and there's I wasn't going through my thing. There's the torsional stress. Okay. The twisting motion. And there again and there's your tau. The torque, which is force per unit, force times the distance, and that's also measured in foot-pounds in the U.S. customary. Okay. Here is the bending force, where he's sitting, the underneath side of that plank is being tensed, tensional forces pulling that way. The upper part is being compressed where he's sitting. Okay. And there's the example of that. The lower part of the board plank is a tensional force. The upper part is a compressional force. Okay. And this, I saw it in the book, and I'm trying to figure out what in the world that is. Oh, it's a foam, a flexible material, can easily demonstrate the types of stresses on solid materials. Okay. You can imagine playing around with that some. Okay. Now, before we get there, let's go back to example 1. And I think what I'm going to have to do is go back to my other slide. All right. Whoa. Example 1. A steel column in a building has a cross-sectional area of 2,500 square centimeters. So they didn't say how that column was. You want it to be a circular column or a rectangular column, square column? How do you want to express it? It doesn't really matter, just so I can draw it. Huh? Square. Okay. So let's just say, let me get my pen back. Okay. All right. So let's say it's a square column. This is the cross-sectional area of it. Ooh, that's not very smart, but something like that. The cross-sectional area, A, is equal to 2,500 square centimeters. Okay? The first 0 is significant. The second one is not. It supports a weight of 1.5, so this is a column. Okay? It's supporting a weight, or a force due to weight, of 1.50 times 10 to the 5th, pretty big, Newton. Okay? Find the stress on the column. How do we measure stress? It's what? Yeah.
Are you asking what unit measure?
Pascal will be the unit, but what is the formula for it? Force per unit area. We've got both of those. The thing is, though, a Pascal, remember, the units for that is newtons per square meter. We've got square centimeters. So the question is whether you want to go on and convert the area to square meters or work the problem and then throw it in. They like to throw it in at the end. I just as soon do it here. Okay? Let's multiply this by a conversion factor, and we want this in square meters. Okay? So what unit is going to go where? The first blank is for your numbers. Leave those alone now. Put the units in their place. What goes on top? What goes on bottom?
100 centimeters. Well,
okay, just, yeah. Which unit goes where?
centimeters will go on the bottom.
Yeah, centimeters on the bottom and meters on the top. And you're absolutely right. 100 centimeters is 1 meter. But we've got square centimeters and we're going to square meters. So what we have to do is square everything in sight. Okay? Well, 1 squared I can do. That's 1. Anyone know what 100 squared is?
No.
Say again? You double the number of zeros. So it goes from 2 zeros to 4 zeros. That's 10,000. Okay? So the square centimeters go out, and you're left with square meters. 1 squared is still 1. So you divide 2,500 square centimeters by 10,000 square centimeters per square meter, and you come out with, that basically is moving the decimal 4 places, so that's 0.250 square meters. That's a quarter of a square meter. Okay? Now we can put this in their place. Okay? This will be a force of 1.50 times 10 to the 5th newtons divided by 0.250 square meters. Okay? If you got a calculator, do that and see what you come up with. It's going to be a pretty big number. Remember how to do scientific notation? The EE or EXP key. Now, I could almost probably do this in my head. Yeah. I'm going to move this decimal 2 places that way, that one 2 places that way. 25 will go into 150, 6.00 times 10 to the 5th. I think that's right. Pascals. Or, if you wrote that in kilopascals, that would be 600 kilopascals. Is that what y'all got, or did you get 6.0 times 10 to the 5th? Did you? Huh? No, you may. I'm doing it in my head, so I may have gotten it wrong. What did y'all get? Yeah, 6.00 times 10 to the 5th pascals, or 600 kilopascals, and you should put a bar over that. Was there a question of how we got that? Okay. Now, when you're doing scientific notation, don't do times 10 to the 5th. That might screw you up. Use that EE or EXP key. Remember how to do that? Is that where it's messing up? What's that?
Yes, I did my E. I said
Divided by 0.25. That's, if you're using the top without my moving decimals and stuff, it's 1.50 EE or EXP5 divided by 0.25. Okay. Anybody need it? That's quite a bit of pressure. Okay. 600 kilopascals. Now, a kilopascal is not quite the same as a PSI, but they're close. So this is a pretty hefty number. The book did all that verbiage in between, and now go back and, I mean, there we talked about all these different, well, I mean, they were all stresses, okay? I guess that's why they were doing different kinds of stresses. This doesn't look very good. There, I needed that. Okay. It was somewhere back there. Okay. Everybody got it now? Or still not? You got it? Huh? Right. Right. Okay. Do you need help with the calculator? You think you got it?
No. You showed me, so I need to know how to do my E.
Okay. Okay.
So it's actually.
Yeah.
Oh, you have to put it.
Yeah, you put 5. Yeah, you put 5. Okay. And then divide that by
That's right.
your 0.25. The exponent goes after the EE. Just the exponent, not times 10. And then if it gives you something in scientific notation, then you put the times 10 instead of the E. So that's why when you finish it, it's going to come out 6.0 E. It's 6 E5, right? Is that what you got?
Yes.
And that's why. Okay. Now we're going back to the concept of elasticity, which seems like it was pages ago. The guy who came up with this was a guy who was a little bit older and more senior than Isaac Newton, but I believe he was living about the same time. He was an English scientist, and he was a honcho. He was one of the top scientists in England until Newton came along, and Newton blew everybody out of the water. And they didn't necessarily get along that well, mostly because Newton was just really superior to just about everybody. And he didn't mind telling them. I mean, he wasn't totally obnoxious. He just didn't have good people skills. Okay. So Robert Hooke came up with what we call Hooke's Law, and that is, and let's see, I think the next slide, so let me discard this and go back to, where is it? There it is. There. Oh. Concurrent slide. Okay. And this is Hooke's Law. This is a graph of Hooke's Law showing the behavior within and beyond the elastic limit. Okay? Now, they always illustrate it this way, and I'm sure there's got to be a reason for it, but most of the time I like to put the independent variable on the horizontal axis, dependent variable up here. They do it the other way. The applied force is the independent, that's what you're applying, and then the result of that, the dependent variable, is your change of your length, change of your, whatever is being displaced, okay? And basically, Hooke's Law says, is expressed this way. Well, let me read it to you first. It's in the text. The ratio of the force applied to an object to change its length, resulting in being stretched or compressed by the applied force, is constant as long as the elastic limit has not been exceeded. So basically how you express that mathematically, let me get my pen back now. Every time I change, I lose it. Okay, here we go. So the ratio of the force to the distortion, delta L, is a constant, as long as you're within the elastic limit. So in other words, the graph of the force, applied force to the distortion there, is a straight line because that's a constant slope. However, somewhere up here you'll reach what they call the elastic limit, and now you add more force and you get a lot more distortion. A little more force gives you, you're bent. You're no longer bouncing back, you've now distorted. You've now bent, destroyed, and it's not going to come back. We call that the plastic region. This is the elastic region, that's going to come back. The plastic region, you're going to have a dent. You're going to have a wrinkle. You're going to have a stretch. You're going to have something that doesn't come back. If you keep applying the force to it, remember that spring? Okay? If it got so it wouldn't come back, you're in the plastic region. And that's when your spring gets all distorted. It doesn't come back to its shape. But then you keep pulling and you actually break it. That's in the fracture limit. Okay? So, that was describing what we were seeing with the spring earlier, and that's as long as you're within that linear region, you're in the elastic region. And there, Hooke's Law applies. You get outside that, Hooke's Law doesn't apply anymore. You're exceeded that. So let's do example 2. Let's see if we have, no we don't. Okay. Let's do it here. So here we go again. All right. A force of 5.00 Newton. Whoa, let me get my pen back. Keep forgetting. Have to do this. The force of 5.00 newtons. Okay? is applied to a spring whose elastic constant, also called spring constant, also called Hooke's law constant. That constant is 0.25 newtons per centimeter. Okay? So the K that we had in the earlier thing is 0.25 Newton per centimeter. Okay? Remember how that went. The F over delta L is equal to K. So this was in newtons and this was in centimeters. Newton per centimeter, that's what K is measured at. In the U.S. customary, it's probably going to be pounds per inch or something like that. Okay. Find its change of length. Okay? So we're looking for what? The delta L. That's supposed to be a delta. It's a pretty ugly delta. Delta L, that's the thing we're looking for. Well, we have the formula. F over delta L is equal to K. That's Hooke's law formula. The K is here, the F is there. You can either solve for delta L now and then plug in. I call that chug and plug. Or plug in now and solve. I call it plug and chug. Whichever you prefer. Want to solve for delta L or plug in the numbers and solve that. I don't care.
I think it's easier to solve for delta L.
Okay. And how would you do that?
I would say delta L equals constant times force.
Okay, not quite. What you have to do is the rules that you obey in mathematics. Okay? Multiply. You see, what's wrong with delta L is down in the denominator. We don't like it down there. So let's multiply delta L to get it out of the denominator, right? But if you multiply on this side, you have to multiply on this side as well. So now it wipes it out here, right? Okay? So now we have F is equal to K delta L. That's an ugly delta. I don't know why they're coming out so bad. What we're looking for is delta L, so we want to get rid of the K. This time we'll divide by K. Because it's multiplied there, let's now divide. So it goes away there, shows that delta L is equal to the force, which is 5.00 newtons, divided by K, which is 0.250 Newton per centimeter. Okay? Now, that's going to give you your delta L in what units? Well, the newtons are going to cancel out, and 1 over centimeter is going to be centimeters. So if you do 5 divided by 0.25, again, I'm going to use the same trick I did before. Move this decimal 2 places here, this one 2 places there. 25 will go into 500. Well, 25 will go into 50 twice, and then, so that's going to be 20. So that's going to be 20.0 centimeters. Because you had 3 significant digits everywhere. So 20.0 centimeters. Everybody see that? No? How I did the math or why it works?
Oh, you know what? I was trying to remember at the very beginning when you told us about the Navy way.
Oh, okay. Yeah.
You know,
Okay.
I was trying to remember what you said.
Okay. The one on top is the one that stays on top. So, you like triangles or circles? Triangles fine. I like triangles too. Okay. Okay. Put the F on top because that's where it is. Then put the K delta L down here. It doesn't matter which one. Delta L here, K here. And the reason that that works, you know, our original formula is this one. F over delta L is equal to K, which is right here. Cover the K, and K is equal to F over delta L. So that's how it works. So now to get L, you do F over K. And that's exactly what we did here. Force over the K. So yeah, that works too. And you don't have to think about it and move things around. Yeah. That clear it up? Yeah. So yeah. always put, if you have the ratio like this, whatever's on top, that goes on top there. The other two go down below. Okay, good deal. I hadn't even thought about doing that, but yeah, that's a good way to do it. And did I do my math right? 5 divided by 0.25, did you get 20? Yeah, okay, good. 20 centimeters. That's quite a, yeah, that's about 4 inches maybe? No, more than that. 8 inches probably. Okay. That's a fair amount of movement. 2.54 centimeters in an inch. So that's a little bit less than 10 inches. So I'd say about 8 or so. Just to give perspective here. And that, by the way, was a spring. I didn't draw my picture. I should have. Here's a spring with nothing on it. And then you put a 5 Newton mass on it, and it stretches it down there, as long as you're within the elastic limits. Okay, so what we're looking for is this is your change of length, delta L. It was up here with nothing on it, with the 5 kilograms. It's down here. Okay, so that's the delta L, with a spring constant of 0.25 newtons per meter. Okay. Yep, 20.0. I see it now. All right. Example 3. Red-eyed. Can I erase this one? Everybody got it? Okay. A force of 3.00 pounds stretches a spring 12.0 inches. What force is required to stretch the spring 15 inches? Okay, so here we have again a spring, a pretty tight spring here. Okay, and when you put a force of 3 pounds on it, it stretches it here a delta L of 12 inches. And this was a force here of 3 pounds. And by the way, that's a force. Okay, weight, force you to weight. Okay, so what can you get from that? We have we have 2 of the 3 pieces of your Hooke's law. What piece are we missing? We have force and delta L. What are we missing? The constant, yeah, K. And how is K related to force and displacement? F over delta L is equal to K. That was our original Hooke's law formula. So let's just do it and see what we get. 3.00 pounds divided by 12.0 inches, and that gives us 0.25. They like that, don't they? 250 pounds per inch. That's your spring constant. K. Hooke's law constant. Elastic constant. Whatever you want to call it. Okay? 0.25. Now you can answer the second question. What force is required to stretch the spring 15 inches? So now we're looking for force. We don't know. The new delta L is going to be the 15 inches. And we already know the spring constant because it's the same spring. Okay? And we assume we're within the spring constant. So this is 0.25 pounds per inch. Okay? Now, you can use your Navy way or you can use any way you want to. How do we find force?
You multiply the change in
by the K, exactly. F is equal to delta L times K, or K times delta L, doesn't matter. So that would be 15.0 inches times, and units are your friends, folks, 0.250 pounds per inch. Look at that, the inches cancel out, and that leaves you pounds, which is a great thing to measure force with. And let's see, what will that be? A quarter of 15 would be 4.75? 3.75, I can't think. Okay, 3.75. Okay, 3.75 what? Pounds. Yeah, there's your unit. 3.75 pounds. So 3 pounds will stretch it 12 inches. 3.75 pounds will stretch it 15 inches. Good deal. Okay. Now let's get to one of those big old building problems. Okay. All right, to erase? Yay? Okay. A support column is compressed 3.46 times 10 to the minus 4 meters. That's not much, folks. Okay? That's 0.346 millimeters. Okay? Now let's see if I got a dime. Yes, I have a dime to my name. Okay? That is about a millimeter. Okay? 0.346 would be about a third of a millimeter. So this is not much compression here. But you don't want it to be very much. You want that metal to be pretty strong. But it still is compressed. A support column is compressed 3.46 times 10 to the minus 4 meters. So that's your delta L. 3.46 times 10 to the minus 4 meters. Really small amount. Under a weight of, here's your force, of 6.42 times 10 to the 5th newtons. 6.42 times 10 to the 5th newtons. A lot of force. How much is a column compressed under a weight of 5.6? Okay, so now you're going to increase from 642,000 newtons to 5.8 million newtons. Okay, that's what we're talking about here. So the question is, what is going to be the new delta L, the unknown, when the new force goes up to 5.80 times 10 to the 6th newtons. Okay? What you think you better do first?
Figure out the constant.
Yes, that's what they suggest you do. Okay? You can do it otherwise, but yeah. So, what is the constant? What's the formula for it? Force
Divided by change in
delta L. Okay? So that would be 6.42 times 10 to the 5th newtons divided by, thank you so much. All right. Chapter 8. Good deal. All right. Gotta move on. Okay, there's my pen. Divided by 3.46 times 10 to the minus 4 meters. Now, folks, expect a pretty big number here, because already your numerator is large, but your denominator is tiny, so that's going to make this constant an enormous number. Something on the order of 10 to the 9th. I don't know if it's going to be quite 10 to the 9th. I think it will be. 3 or 2 point something times 10 to the 9th, maybe. Anybody got it? Oh, 1.82? 1.826?
No, 1.86.
Okay, what's the next digit? Or does that come out exactly? What's that? 1.866? Just. Yeah, we only do 3. Did you already round it?
Yeah.
Oh, okay, good. 1.86 Newton, oh wait, times 10 to the 9th? Yeah, 10 to the 9th Newton per meter. Take that and multiply it by, no, okay? You want to know what the delta L is. So the F sub n, or you can use your Navy way, over delta L is equal to K, and this will be the new one and the new one. So the delta L new is going to be F sub n divided by K. Same K, okay? So this will be, the new force is 5.80 times 10 to the 6th Newton, and divide that by your 1.86 times 10. And basically, if you still have that big old number on your screen, you can use that big old number. You don't have to round it yet, and then see what you get. But just for, I didn't want to write all those digits, times 10 to the 9th meters, okay? And what will that give you? The new delta L is going to be what?
3.12
times 10 to the negative 3, and that would be meters. And let's see, you got newtons divided by, I put the wrong unit, Newton per meter. The newtons go out, and that gives you meters, right? So, whereas before it was compressed, something's not making sense now. Oh yeah, I'll use a nickel. Okay, it was compressed about 1/3 of a meter. Now you're compressing it 3 millimeters. So I would need 3 dimes. I don't think I only got 2. I don't even see 2 now. But I'll just use 2 nickels and a dime. Whereas before it was compressed 1/3 of a meter, now you're compressing it millimeter. Now you're compressing it about 3 millimeters. 3 times 10 to the minus 3 is. Okay, is that what they got? 3.12 times 10 to the minus 3 meters, or about 3.12 millimeters. All right. Now, there's a little physics connection there about development of materials. They choose materials based on 2 main factors, cost and strength. That's true. My dad was a agricultural engineer, but he talked about strength of materials, strength of materials. That was one thing he learned. They really drilled it in him. It's a pretty nice thing to read. I'll let you read about that. Late 19th century, an American engineer constructed the first steel arch bridge, not making it out of rock anymore, stone. And I think that picture of that one, no, this is a cast iron bridge across Brookdale, England, and this was 1799, and I guess it's still operating today. Good for it. So what they do, and they talk here about putting reinforced, pre-stressed steel into the concrete to make it stronger. All right, problem set 12.2. Have quite a few there. Do any of the odds 1 through 19. Do some of each type till you get a pretty good feel that you know what's going on with solids. So let's move now. Let's see. Let me go away from there. I may have stayed away too long. Let me see. Go back to this one. Whoa, where did you go? Get back up there. Okay. From current slide. All right. Oh, and there's that bridge I was just talking about. They used cast iron, which is pretty brittle stuff, but evidently it's lasted since 1779, so not going to argue with that. 250 years, pretty close to it. All right, 240 anyway. The columns there are made out of stone, though. That's what's supporting everything. Okay, and then this is a picture of how they reinforce concrete. They put tension on the steel bars, pour the concrete, get it set, and then release the tension, and that pulls it even tighter. So it really strengthens the concrete, supposedly. However, there's something that goes on with concrete and steel. It actually aids in the deterioration of the steel, you know. So after so many years, they have to replace that, usually decades later. And that's why some of the bridges need to be repaired and replaced, because the concrete with the steel reinforcing, it actually loses strength over time. It keeps it for a long time. Yeah.
When they do the piles
Yeah.
under the water,
Right.
how does that concrete dry when it's,
Yeah.
how does that occur?
Well, sometimes it's just steel under there. Other times they do dry. What they'll do sometimes, I read a book about this, I think it's they put a well around it, keeping the water out, and let all the water drain out, and then pour the concrete in, and then let it set and make sure it's nicely set before they remove the well, the casing. I think that's how they do it. I'm not sure, but usually what they've driven, though, is not the concrete. They drive the steel, you know, down there, and it's pretty substantial. But even in doing that, they usually have a case around it and they may just pour into that and then lift the case off later. Because concrete does shrink a little when it cures, because the water evaporates or drains out, and then it shrinks a little bit. Okay. Now we get into properties of liquid. Okay? I think we talked about some of these before, but if not, yeah, I'm pretty sure we have. As noted previously, a liquid is a substance that has a definite volume but takes the shape of its container. The molecules move in a flowing pattern past each other, but they stay in a close proximity to each other. That's why it keeps its volume but takes the shape of the container, because they are free to move around. Okay. Now, most liquids share the following common properties. There's two types of attraction. One is cohesion, and think of the CO word like cooperate, compress, CO means coming together of the same types of material, okay? If you're cooperating with others of your thing, anyway, that's cohesion, the tendency. Water molecules love other water molecules. They stick really close to other water molecules. However, they also are attracted to other molecules. So they cohese well and they adhese well, okay? The cohesion, cohesion, force of attraction between like molecules, causes a liquid like molasses to be sticky. Adhesion, the force of attraction between unlike molecules, causes molasses also to stick to your finger, okay? If you were to jam your finger down in molasses real fast, you're almost going to jam your finger because it doesn't like to separate that easily. But when you do jam it in, then it sticks to your finger, so it adheres to your finger. Okay? And this is I didn't think of doing this, but you really could. Water has this incredible attraction to its own molecules, and that's called surface tension, okay? If I had a container of water here, and you can probably do this at home, I'd do it in a sink. Pour water, say even that glass there. Just pour it full of water until it looks like it's full. Then pour a little more, and pour a little more. You'll be surprised how much more you can pour before it spills over, if you do it really slowly, because you'll actually see almost like a dome of water. It's not that much, but a little bit. You'll see water over the top of the glass because those water molecules are hanging on to their neighbors and not letting them spill out. But you get too much and they finally spill. That's called surface tension, okay? I think I've used the example before. If you've ever dived into a pool and done a belly flop, you'll feel the surface tension of water. It doesn't feel good, okay? It hurts because water molecules don't like to separate that easily, okay? Now, the example they show here in the book, if you drop a needle very carefully into water, it actually floats on the water, okay? Now, they don't show this figure here, okay? But it's in your book. It will float. And you know steel doesn't float, okay? But it will because the surface tension is holding it up. And then what they say you can do is take 1 drop of soap, liquid soap, surfactant, dishwashing liquid, something like that. Drop it in there, the needle will just fall to the bottom. Because what a surfactant does, or what soap does, it doesn't really clean. It does, but what it's doing is making water wet better. Now the water molecules don't want to hang on to each other. The surfactant gets in between the water molecules and separates them. Now water can get right up next to the dirt and get it out of there. Whereas before, it's hesitant to do so. Okay? That's a strange way of saying it, but it's true. Okay, so that's surface tension. That's that little illustration there. Now, do not do this one at home. Do not do it anywhere. Don't drop some liquid mercury on a surface. If you do, you'll watch it beat up. It looks like it's a ball bearing until you touch it, and it's a liquid, you know, but it just doesn't like to adhere to anything else. It only wants to stick to itself. So it forms the tiniest little surface area it can for that volume, which is a sphere. So mercury will beat up like crazy. I can remember when we were young, I never had any, but someone would bring some liquid mercury to school, and it was just fun to watch and to play with. You probably did it too, huh? Huh? Yeah. Not good, though. Yeah, because mercury is a heavy metal and can, usually for adults it's not too bad, but you don't want kids doing it because that can mess with maturation, you know, of things. Now, a liquid drop in space is a perfect sphere because there's no gravity pulling it. But when you get on Earth, you get that little teardrop shape because the bottom is being pulled more rapidly than the top. So just other examples of adhesion, cohesion of water or any liquid. All right, so that's adhesion and cohesion. The next of these is viscosity. Anyone ever heard the term or used the term before? Where?
Well, wine has viscosity.
Oh, really? Okay, well, I know it does, but I didn't know that was something they measured.
Well, you can measure, like, especially like red wine, as far as when you tip it,
right.
If it leaves kind of, you know, sort of, I don't know a better word, like tendrils on the side
Right.
of the glass,
Right.
it's supposed to be better.
Right.
Because of the viscosity of it.
Oh, wow. I did not know that. That makes perfect sense because then it's richer, fuller. Yeah, okay. I would guess red wine would be more so than white wine, right?
Right. You don't see it really with white wine.
Right. Okay. Of course, it's hard to see white wine, too. Yeah, right. Okay. All right, so that's viscosity. Another place, more of a, I guess, a guy thing is oils. Have you ever noticed on cans of oil those numbers? 10W40, 30 weight, that's a viscosity number. Okay? Now you want your oil to be somewhat viscous because you want it to coat all the surfaces. But you also don't want it to be too viscous because if it's too viscous, it's hard for the materials to move in it. So you want to have a good mix. So some places, like in Minnesota, where you can have really hot days in the summertime, not quite as hot maybe as here, or maybe some days it's actually as hot as here. But in the winter times, they get way colder than it does here. So their range of temperatures are huge. They actually will have to change the oils in most of their vehicles completely in between winter and summer. A low viscosity oil in the winter, because the lower temperature makes it more viscous, so a low viscosity oil in the winter, but if they use that low in the summer when it gets really hot, then it doesn't coat as well. So they actually change. So a lot of times people are going more to the blended oils that have a variety of viscosities mixed together, so that some of them will always do so. Anyway, that's viscosity. Okay. Now, and they show cold oil and hot oil here in the figure. We don't have it here. Another characteristic of a liquid, and it has to do with both of the things we talked about before, is what we call capillary action. Okay? When you hear the word capillaries, what do you think? Anything particular? Say again?
Blood.
Blood, exactly. And there's a reason for that. Your transport, your superhighways for blood are your veins and your arteries. Okay? They're just there to pump large quantities of blood. But where the rubber meets the road, where you're actually using that blood, are in the tiny little capillaries that come off of those. Okay? And these are so tiny, such thin walls that now the oxygen can move across the cell membranes. Everything that's happening goes across it. The capillaries are so incredibly tiny. But that's what a capillary, the smaller the diameter, then actually the harder it is to get blood to move through them because the walls are so close together. Okay. Well, that's what capillarity is, and this is what this is showing here. Now, the top figure here shows number one, a liquid keeps the same level in tubes large enough in diameter that are connected. So, in other words, a little tube, a tube with bulbs in the middle of it, a cricket tube, or a test tube, they're all going to reach the same level because liquid goes to the same level. Unless you get small enough tubes, they become capillaries, and now they'll go to different levels. Okay? Liquids rise in thin tubes because of surface tension and adhesion. The water likes to stick to the glass or the plastic, whatever the tube's made of, so it pulls it up, but the surface tension, it pulls the rest of the molecules up, and actually that adhesion pulls it up the very small tubes. Now, I think somebody, said have you ever taken blood? I think diabetics do this, do a little pinprick, and then get that capillary tube and just hold it there near where the blood is. It just goes right up the tube because of adhesion. That's capillary action. Okay. That's what's happening. And that's what the figure over there is showing. You can tell which is the smallest diameter tube by how high the water goes in it. Okay? Now, yeah. We're going to start next time at the figure 1225, which is the one that's in the book, and that will show more of this capillary action. So we'll look at that starting next time. And then we'll move right into properties of gases. There's no problems given for properties of liquids. The property of gases, even smaller. And then density, there we'll get a lot more problems. Okay. Good deal. All right. Any questions? Good class.